Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. Today is lesson 1.10, which is on advanced projectiles. Now, this topic, or today's lesson, doesn't cover anything new, actually, but what it does is it goes into projectiles into a little bit more depth and look at some of the more complicated problems that you will encounter with projectiles. So we'll look at how we deal with those kinds of things. So the first thing that we're going to do is just look at projectiles, and just in general, projectile is just something that's launched at a certain angle above the horizon, and it could be just on a flat surface like this, or it could be at the top of a cliff like this. You basically treat deal with the problems in the same sort of way. There's just a couple of slight differences between them. First of all, we decide where our origin is going to be, and usually that's just going to be at the launch point. So generally speaking, just make the origin your launch point, and the projectile is launched at a certain angle, and then just recognize too that the component of velocity, the initial component of velocity in the x direction, is just going to be v cos theta, like so. And that goes for both scenarios like this. And then the same thing for the y direction. The initial velocity component in the y direction is just going to be v sine theta. Right? So x direction v cos theta, the y direction v sine theta. And the other thing to note is that when you're dealing with a question like this at the top of a cliff, the displacement, if you make this your origin, the displacement is going to be a negative number here. And so just make sure you watch out for that if you're dealing with a displacement that's below the horizontal. So let's look at, oh, and also one other thing is that when the projectile is launched and it comes to rest at the end of its trajectory, whether it's here just down on a flat horizontal surface, or whether it's down below the top of the cliff here, the range is what's referred to as the distance that it goes in the x direction. All right, so that goes for both of these kinds of scenarios. The range is just simply the distance that the projectile goes in the x direction in both of these different scenarios. So if we take an example with some numbers here, and we have the example here where a projectile is launched at 65.2 meters per second at 34.5 degrees above the horizontal. So if you're given a problem like that, again, the first thing you're going to do is start with a diagram like this, and it's either going to be on a flat surface, which is just horizontal, or you're going to have a cliff. It doesn't really matter too much. You're going to deal with the problem in the same sort of way. And again, like I mentioned, the only difference being is that if you go below the horizontal, then you're going to be dealing with negative numbers in the y direction, and that's okay. That's not a big deal. So a problem like this, what's being asked of us is to find what is the velocity and the displacement vectors at 1.5 seconds. And this is one of these kinds of typical kinds of problems that you will see. And so we need to determine, okay, well, what's our after 1.5 seconds post-launch, what will the velocity vector be, and what will the displacement vector be at that time? All right. So again, start with our diagram here, and then just write down what it is that we know. What do we know about this? Okay. Well, the velocity in the x direction is just going to simply be 65.2 cos 34.5 degrees. So that'll be the x component of our initial velocity. And then we can determine the y component of our initial velocity, which is just simply 65.2 sine 34.5 degrees. So there's our initial velocities in the x and y directions. So we have those components. And so now it's just a matter of determining, okay, well, what's the velocity in the x direction and in the y direction at 1.5 seconds. Well, at 1.5 seconds, so that's our time. the acceleration is just going to be in the y direction. There's no acceleration in the x direction. And that's going to be minus 9.8 meters per second squared. And again, that's just in the y direction. The velocity in the x direction is not going to change. And so it doesn't matter what time you're looking at the velocity in the x direction. It will always be the initial velocity. So the initial velocity in the x direction we already calculated was 53.7 meters per second. So that was pretty simple. Okay, then the velocity in the y direction now, we'll make use of this formula right here, or this equation. And again, you will always be given these formulas and these equations. So this is the one that's going to help us here. The velocity in the y direction is just going to be the initial velocity in the y direction plus at. And so we just do that calculation there, and we get 22.2 meters per second. So now we have, at 1.5 seconds, our velocity in the x direction is still 53.7, and the velocity in the y direction is 22.2 meters per second. And now we want to put our resultant velocity vector into polar form. And so we'll make a little diagram here. Let me just move this out of the way here. Let's put it up here for now. And so here's our resultant velocity vector here. I'll put a double line on here because normally our resultant vectors, we make it a double line. So here's our resultant vector. We have 53.7 meters per second in the x direction, and we have 22.2 meters per second in the y direction. And now it's just a simple matter of using Pythagorean theorem and the inverse tan function, and I trust that you can do the math on that. So our velocity vector at 1.5 seconds turns out to be 58.1 meters per second at 22.5 degrees. Make sure I got that right. Check my numbers here. Yeah, 22.5 degrees north of east or above the horizontal. Sometimes you can just use, just say above the horizontal when we're dealing with projectiles like this. So there's our velocity vector, so that takes care of part A. So at 1.5 seconds, here's our velocity vector. And the second part now is what's our displacement vector now at 1.5 seconds. And so in the x direction, because there is no acceleration, we can just simply use displacement, or sorry, that would be a velocity times time. Let's change that right now. My apologies. That should be velocity times time. So that would be the initial velocity in the x direction times the time. And so that would be 53.7 times 1.5. So the displacement in the x direction is 80.6 meters. Now we do have acceleration in the y direction, so we can't use that equation for the y direction. So we have to use this one here. So displacement in the y direction is the initial velocity in the y direction times t plus 1/2 at squared. And again, that's just one of the equations formulas that we've been working with lately. And we just need to put the numbers in there. And so we get, I trust that you can do the math. Make sure, be careful how you punch it in your calculator, but you should get 44.4 meters. So the displacement in the x direction is 80.6 meters, and in the y direction it's 44.4 meters. And then once again we can find our resultant vector, again with our y displacement here, our x displacement over here, and our resultant then will be, as it turns out, 92.0 meters, and then at the angle theta here, it works out to be 28.8 degrees. And again, this is north of east, so it's above the horizontal. Now, as it turns out, both the velocity and displacement vectors turn out to be above the horizontal. If it was below the horizontal, then the y number would be negative. So if the displacement then is below the horizontal at the certain time that you're trying to find that out, then this would be a negative number and not a positive number, and that would be the only difference. All right, so this is a typical kind of problem. Yes, there's a fair amount to it. But as long as, and again, what you really have to keep in mind is separate the X and Y directions. And if you can keep that straight, then that'll go a long way in helping you to solve these kinds of problems. This is more of an advanced kind of problem, as we said, but this is a type of problem that you will see in this topic.